algebras are certainly certain algebras which are defined recursively. And I will give some examples in the next few minutes. They are inside a ring of fractions in n variables, say x1 up to xn. What is important is like the recursive definition. So you start with a fixed set of numbers, variables, which are n here, and then you start replacing them one by one, and you get new sets of variables. So this gives you overlapping sets of generators, and each set of generator has the same size, this n, and we call them clusters. And all the elements are the cluster variables. So you do this iterated replacement or recurrence relation as long as you want, and there will be many relations between these variables. The exchange between two sets of generators where you replace one generator and get a new one is called mutation. So these cluster algebras were invented around 20 years ago by Fomin and Selevinsky, and they were motivated in the study by phenomena they observed in the study of the dual canonical basis. So this is sort of a discrete object. You have a basis and you can replace one of the elements by some other element, not like in basis in linear algebra. And the other motivation came from totally positive matrices, which were defined around 1930 by Schoenberg. So these are square matrices where all the minors are non-negative, or say positive, over the reals. And in the first 20, 30 years after their definition, the main work was on showing that they have n distinct eigenvalues, which are all real. And then later Lustig generalized that concept to algebraic groups. So that was in the 90s, and that's when Fomin and Selevinsky got interested in this topic. So the cluster algebras are like a framework to study both these phenomena, and they have produced a lot of different areas in mathematics and have answered some of the original questions, but a lot are still open. So let me start by giving two examples. The first one is a classical one, the Pentagon Recurrence, which had been studied already by Abel and Spencer and Hill and Linnes. So you have a recurrence which has elements Fn, which are again fractions in two variables, x1, x2. And the recurrence is that you get Fn plus 1 as follows, like in this implicit relation. Fn plus 1 times Fn minus 1 is the Fn plus 1. And then the initial conditions, for example, could be that F1 is x1, F2 is x2. And by the definition, you have to do iterated fractions. So F3 can be computed as follows. F4 is already slightly more complicated, but it simplifies nicely with this denominator x1, x2. And then you compute F5, which looks very much like F3. So the denominator becomes more simple again. And then F6 is already F1 and F7 is F2. So this this recipe for computing elements gives you iterated fractions, but in the end, it only has 5 different elements. So you have a periodicity. And you can modify the original rule slightly to still get like an 8 periodic sequence or another one. So that's the first thing to observe. And the second thing is that we have nice denominators. So that's the so-called Laurent phenomenon. That the denominators are only monomials in the initial variables. And so in fact, the whole sequence is inside the ring Zx1 with plus minus 1 and x2 with plus minus 1. So they're Laurent polynomials, in fact, even in positive coefficients. That's the positivity. So this toy example already shows us interesting things about the cluster algebra. So what is the cluster algebra in that case? We take all these variables we collect and look at what they span inside the field of fraction. So that already encodes all the relations which we have from the original recurrence relation. Okay, and that's a cluster algebra coming from these two initial variables and from the recurrence relation. So it's a subring generated by all the FIs inside the field of rational functions on x1 and x2. And in fact, any pair of successive elements determines the whole cluster algebra. Because we have this rule, we only need two neighbored elements to get everything else. And we have an exchange relation, so we can drop one of these FIs and get a new one by this relation. So in fact, and that's this blue box, the blue box here tells me how to go from one set of generators to the next set of generators. And in that language, these sets of generators are clusters, and the FI are cluster variables. Okay. And the exchange, this box, is the so-called mutation. So that's the first classical example. Let's look at another player which we've seen this conference is the Grassmannian. So I look at the coordinate ring of the Grassmannian of two-dimensional subspaces in C to the n. I will probably just work over C today because that's better when we go to the categories. So we need an algebraically closed field. This coordinate ring, and I should take the affine cone over the Grassmannian, is given by the Plücke coordinates. And if you want, you can think of PIB AB as EA wedge EB in the second exterior power. And these Plücke coordinates have relations that they satisfy the Plücke relations. So these are the short Plücke relations. They depend on the indices A, B, C, and D being cyclically ordered. Let's say A, B, C, and D. So the product of those two plus the product of these two is the same as the product of the ones diagonally across. So that's the classical coordinate ring of the Grassmannian. And I've drawn it here in terms of a polygon. So we can think of these PABs as being given as diagonals in a pentagon, for example. So this is the example, n is 5. And then the boundary ones are just PII plus 1. And then in classical geometry, there's this result by Ptolemy, which tells us that exactly this rule when we are on a circle and we have a quadrilateral on a circle, that the product of the length of the diagonals is the same as the sum of the products of opposite sides. So if you just think as these diagonals giving you formal variables, PI or PAB, then the Ptolemy rule would tell us that, say, P14 and P35 are in the relation P13, P45 plus P15, P34. And that allows you to go from, say, these two diagonals to these two with all the boundaries, and then just around the whole diagram. So along these edges, I have an exchange of two variables, and I've indicated in the shaded region where this exchange happens. And if you want, you can specialize all these boundary Plücke coordinates to 1, and you get back the previous example. So the Pij or the Plücke coordinates are cluster variables. And here we get the whole coordinate ring if we collect all these cluster variables and look at what they span in that coordinate ring. Now the collections I want, because I said these cluster variables are grouped into collections, are really just the triangulations in this pentagon or in a regular n-gon. And the exchange, well, it's given by this Ptolemy relation, but that's just a flip in a quadrilateral. So we exchange one diagonal by the other, and one diagonal always gives us a quadrilateral. Okay, so this second example is one of the first examples, again, of a cluster algebra, and this is an instance of a more general result. That's the following theorem. So if we look at the coordinate ring, and again, I should take the affine cone of the Grassmannian of k-dimensional subspaces of C to the n, and that result is due to Fomin-Zalebinsky for k equals 2, and then Scott later for k, arbitrary k. So this has the structure of a cluster algebra. I'll explain what that means, and mutation comes from Plücke relations. So having the structure of a cluster algebra means you take some ring and you find inside like a set of generators, fixed generators, and the rule how to replace generators one by one. And then you collect variables by replacing generators iteratively. And in the end, you collect everything and look at what you span. And that should give you the ring you started with. So this is not a straightforward definition, and it's also in general not so hard and not so easy to find that you have a cluster algebra structure. But in case k equals 2, this is just the example of what we had. So the cluster variables that you pick are simply the Plücke coordinates, which correspond to the diagonals in a regular n-gon or a convex n-gon. And then the overlapping sets of generators, these clusters correspond to triangulations of a regular n-gon. So that's an instance where you have a surface, or this is a very simple surface, a disk, and it gives us a cluster algebra structure. So for arbitrary k, we cannot work with triangulations anymore, but again, we find cluster variables among so all the Plücke coordinates are plus cluster variables. And there is a combinatorial way to find clusters. So there exist clusters which consist only of Plücke coordinates, and they arise from certain diagrams, which are called alternating strand diagrams in a disk with endpoints. So it's like this polygon we had earlier, but now we don't take triangulations, we take something which is called alternating strand diagram, and I'll explain that on the next slide. So the Plücke coordinates are among the cluster variables. What I mean by Pi, you can think of if I is some k subset in 1 up to n, then you can think of this as being ei1 up to eik in the exterior algebra. So these are the Plücke coordinates. They are all cluster variables, but in general, for arbitrary k, so there are infinitely many cluster variables in general. So only when k equals 2, the cluster variables are exactly indexed by the diagonals in a polygon and the edges. When k is 3, there are 3 more cases where we have finitely many cluster variables under this process, but then outside of this range, we have always infinitely many cluster variables. So even if we say we take some diagram or triangulation to produce cluster variables, or that all the Plücke coordinates are cluster variables, there must be a lot more. So this is never going to be everything, but there are nice ones, and they tell us a lot about the cluster algebra structure or the cluster category structure, as we will see later. Maybe one thing about these cluster variables. So in general, there is work of Thomas Booker Price, who showed that there are cluster variables in every degree for every integer, positive integer. Okay. So what is the philosophy behind using surface combinatorics and cluster to understand cluster algebras or cluster categories? So we've seen this example of the Grassmannian of planes in C to the n. And all the Blücher coordinates are these cluster variables, which we would want to have for the cluster algebra. The overlapping sets come from triangulations, and mutation is Ptolemy relation. But there is a nice geometric approach by just taking an n-gon, taking diagonals in it and edges, taking triangulations as these nice collections. And the flip replaces me one variable by another. So this works more generally for surfaces. As Fomin, Shapiro, and Thurston have shown. So basically you can start with an arbitrary surface with points on certain boundary components, like the disk was a toy model, and then you start drawing curves between them, and the curves give us cluster variables, like the diagonals, and then the triangulations will give clusters. A mutation comes from the flip in the triangulation. But then on the other hand, to a cluster algebra, there are also often cluster categories associated to them. And the first approach here was given by Buanmarsh, Reinecke, Reiten, and Todorov, and Galdero, Chapoton, and Schiffler in type A. So a cluster category is another algebraic object. This is a category of modules, of objects where each of these objects, if you look at indecomposable objects, they should correspond to the cluster variables. So you have indecomposable objects, cluster variables. And then these overlapping sets will be a collection of indecomposable objects, which are maximal in some sense, maximal rigid objects. And then you have an operation, which is a mutation again. We'll see that in a few slides, how that works.
Oh, Karin.
Yes.
There's a question that just appeared in the chat from Theo.
Okay.
Does the interpretation of cluster variables as lengths hold in some high generality?
As like lambda length, or as length in diagonal, well, as in relatively high generality, whenever you can get a cluster algebra from a surface, yes, and then it's the Ptolemy relation, yeah. But there are other cluster algebras which are not coming from surfaces.
Okay, thanks.
Yeah, you're welcome. Yes, but the surface approach has been very fruitful. For example, in the beginning, in my first example, I said, well, we have these nice iterated fractions and they still had positive coefficients. And so there was a certain positive conjecture that once you start with a set of generators, you start replacing, that you always get a numerator with only plus signs. And the positive conjecture was, I mean, one of the ways to prove it was to use surfaces. That didn't do the full generality, but that went a long step towards it. And so other nice points about having a surface model is, for example, if we have two diagonals, or in general surfaces, it might be curves, and they cross if and only if the two variables are not compatible, which means they shouldn't belong to a common generating set. And in the category sense, it would mean the two objects have non-trivial short exact sequences between them. Again, they are not compatible. So I will explain a bit how this works for the Grassmannian, again, using surfaces, but we cannot expect triangulations when we go out of the range, when we go away from k equals 2. For that, I have to explain what these alternating strand diagrams are. And this is a notion introduced by Posnikov around 2005, I believe. I'll restrict to k at most and half. That makes it easier to say really what is a finite type. Okay, before we had a polygon, now I work with a disk, call it dn, which has n marked points on the boundary. So I have an example here, 7 points, 1, 2, 3, up to 7. Then there are n oriented curves between these boundary points. For example, you see near point 1, I have a curve going in this direction and going out at 4. They will cross in the picture, so this is different from the triangulation. Crossings should be transversal multiplicity 2, and they should alternate. So if I walk along one of these oriented curves, which are called strands, I should see the other curves which I cross alternatingly from left and right, etc. They're forbidden subgraphs, so we don't want to have two parallel curves which intersect twice. And we never want to have self-intersections. And of course, this is all up to like moving around a bit, so up to isotopic fixing endpoints. And then there are two reduction moves. If I find two strands which like give a small diagon, an oriented one, I can straighten them a bit to get rid of these intersections. Or if I have two strands which come from a boundary point and then cross without having things between, I can also straighten that. So that's a general setup. This has been used by Posnikov in the study of positivity. Now I want to restrict this a bit. So if the permutation that you get from such a diagram, the permutation coming from the vertices, I have n vertices, and like the strand sends me vertex 1 to 4, then 4 goes to 7. And so the permutation would be 1, 4, 7, 3 in cycle notation. So if that permutation is quite homogeneous, just adding k in each step, we call the diagram a kn diagram. So that's important because we want to look at this big cell in the Grassmannian. Now, any such diagram subdivides Pn. Now I called it Pn. Let's change that. The disk into oriented and alternating region, because I assumed that the crossings behave nicely. And for example, there is an oriented region here, and next to it is an alternating region. And what you can do is you label the alternating regions by labels given by the strands or curves. So if I walk along the curve starting at I put the label I in each alternating region. So for example, I start at 1, and then I should put this 1 into that region and this region, and also around the boundary, etc. We'll do this example on the next slide. And you see that this puts in each of these regions puts exactly k labels. K equals T in the third condition. I'm not sure what that means.
In your third condition, you're saying I goes to I plus T?
Ah,
You want I plus K?
Yeah, it's bad handwriting. Thank you. Yes. So this subdivision into oriented alternating strand diagram doesn't depend on the permutation. That's a general fact. And also the labeling procedure works, of course, for arbitrary permutations. And then if we go now to the KN diagrams, what one can show is that every K subset of the labels 1 up to N really appears in some diagram. Not specifically in this one here, but there exists a nice diagram which contains that label. So what Scott did, she showed that if we do this and then you collect the labels, you get the cluster, and that's how you can show you have a cluster algebra structure on this Grassmannian. Let's see how this looks in the example. Maybe like that. I've just copied the diagram, and then I did what I said before, like this curve 1 gives me the label 1 in the regions to the left. And then the curve 2 again gives me the labels 2 in these regions, etc. In fact, I really want it to be reduced, that diagram. So I want to avoid extra crossings. Because what happens if I have an extra crossing, I might reproduce a label. So that's just not reduced. So let's just forget about those. You see, that was a little excerpt from that part, making it non-reduced. Okay. So alternating strand diagrams, and now I'm going to restrict to KN diagrams. But in general, they give collections of pairwise compatible K subsets of N. And if you remember, for K equals 2, we looked at triangulations, and the triangulation is a collection of pairwise compatible diagonals. So now we have a new notion of compatibility. And when are two sets compatible? Or non-crossing? Well, you have to look at I without J and J without I, and then draw them on the disk. I shouldn't do 8 because my example was up to 7. Let's look at 4, 6, 7 and 1, 4, 7 as my set. Well, then I without J would just be 6. Is that correct? Yeah. And then J without I would just be I. And you look at the complete graphs and these complements and they don't cross. So these are just points, they don't cross, and so they are compatible. So any such diagram gives you compatible K subsets. And if I look at KN diagrams, what Scott showed is that a reduced KN diagram always gives you a maximal collection of pairwise compatible K subsets of 1 up to N, and these joint ones. And that every maximal collection comes from such a diagram is a result of O-Posnikov and Speyer. Okay. So this is like a cluster algebra structure for the Grassmannian or for the big cell, but there are cluster algebra structures on related rings. So for Q Schubert varieties, for example, by Serienko, Sherman, Bennett, Williams, or open positive varieties, but more generally by Galashin and Lam. And so that's on the cluster algebra side, but there's also a lot of work, and I'm not citing everything. This is just 2 examples. So there are cluster categories for Grassmannians and for related categories. And the first example is by Geis, Leclerc, Schröer, who have a categorification of this cluster algebra structure using pre-projective algebras. And then Jensen, King, and Su around 2016 is the approach I'm going to use today. This is a very nice categorification of Scott's approach because it gives exactly every of the, say, Plücker coordinates, whereas the Geis, Leclerc, Schröer will miss one. Okay. So I'm going to explain these cluster categories briefly and then illustrate really what that means. So I have to define an algebra and I have to take modules for this algebra. My algebra is depending on a graph, which I call gamma n. And this graph sits on a circle. It has vertices 1 up to n and arrows in both directions. So that's called a quiver, if you like an oriented graph. Yeah, so that depends on n. And then I want to take as my algebra, the path algebra of this graph, which has as a basis all possible paths in the quiver in this graph. So, I mean, the graph has a cycle, and in fact, there will be infinitely many paths. So this is an infinite dimensional algebra. It's going to be a little bit better because we take some relations. So we want that all these short cycles commute. So when I start at some vertex and I do first an x and then a y, is the same as doing first a y and then an x. These are these relations which I have one for every vertex. So x1, y1 with yn, xn, and x2, y2 with y1, x1. So that's the first part. This is just like a pre-projective algebra picture. And the second one I need for the Grassmannian Kn. So this one is whenever I start at the vertex, I want that when I do k steps with the x's, should be the same as n minus k steps with the y's. Again, these are n relations. So I lose a lot of the path, but I can still go on forever. This is an infinite dimensional algebra. And I should also say we really take completed versions of that with respect to the error ideal, but just for the definition, it doesn't really matter a lot. So let's look at one specific element in this algebra. I go along all these vertices and I collect a short cycle. So I take x1, y1 plus x2, y2 plus x3, y3. This element is going to be central in the whole algebra. It commutes with everything. And in fact, this element really gives us the center of the algebra. So the center of this algebra is just a polynomial ring in that T. Again, that's infinite dimensional. And what Jensen, King, and Su did, they defined this category FKN as modules M for the algebra BKN. And they want that these modules are free over the center. So it's like at each of the vertices of this quiver, we have copies of the center and they're linked together by, I have to say how they're linked together with the x's and the y's, but at each of the vertices, I should have copies of the center to make it free over the center. Okay, well, this category, again, in general is not well understood. It's a bit like the cluster algebra for the Grassmannian in general is not well understood, but it does have nice properties. So it is a counterpart for the cluster algebra structure defined by Scott. And we have, again, the Plücker coordinates appear. There are some specific modules which are very nice. which serve as building blocks for the whole category. I call them rank 1 modules. What does that mean? At each vertex of this quiver, I have 1 copy of the center. I have to have at least, yeah.
There's another question from Dari. Is a basis known for BKN?
For BK, well, without the, I guess you just have, no, I think it's a wild. I mean, you have to start trying to find a labeling system for all these paths. But, well, maybe you can do some grading. I haven't thought of that. I guess you can do some grading.
Okay, thanks.
Yeah. Yeah. So because we asked that the modules should be free over this, and it means that at least at every vertex of my oriented graph or quiver, I should have 1 copy of the center. And one can argue that it has to be the same number at every vertex. That is my rank. And the smallest possible thing is that you have 1 copy. So that's why these are the nicest ones. They are the smallest possible modules. And these are going to be the building blocks for the category in general. So if you're familiar with algebras and modules, for algebras, usually, or rings, you have simple modules. We don't have them here. So these are really the smallest ones. And to illustrate a bit how such a module looks like, well, I call it MI in line with the Plücker coordinates. At each of the vertices of my quiver gamma n, I can just give such a module as a collection of vector spaces for the points, the vertices in the graph. And then I have to say how the x's and the y's act between them. So for the minimal one, I just take 1 copy of the center at each of the vector spaces and call it V1, V2, V3 up to Vn. And then I have to say how x acts and y acts. And what Jensen, King, and Su did, well, they defined these modules depending on the K subsets. So on this Plücker coordinate, when you have an element in the K subset, you want that x just is multiplication by 1. So you sort of go from 1 copy of this polynomial ring to another one, and you send coefficients to coefficients. That's multiplication by 1. And if you're not in the K subset, you multiply by t. So you increase the degree. And the y's just do the opposite. So it is quite convenient to draw that in terms of like an infinite cylinder. And here I would think of this center being given as constants, then multiples of t squared, and t to the cube, etc. Now, in my gamma 7, like again, I go back to 7, I would have 7 vertices. At each of these vertices, I want to have a copy of the center. This is a column like this, an infinite column. And I have to say how the x's and y's go between them. I said that x is a multiplication by 1 if my I belongs to the subset. And so really going from 7 to 1, I want to stay with coefficients. So I go from coefficients multiply by 1 and I stay with coefficients. So I don't go any further down. Each of these columns starts with coefficients at the top. But then I can continue, do another x, and now I would multiply by t. So I go away from the top part. And really the top part, which I indicated by green here, is the part where we have degree 0 or coefficients. And if we go parallel 1 bit, you would get things in t and then t squared. And I just did 2 examples. So one is 167 with the definition we had on the previous page. And one is 145. So this top part really tells you how the module looks like. And we sometimes call it the rim. That's like language from Jensen, King, and Su. Yeah, but you see there are infinite dimension modules, but they're quite nice. They're sitting on a lattice, which is on a cylinder. This wraps around, it just goes down infinitely, but it is well behaved. Okay. So how can we use combinatorics to understand this category? Right now it's been described quite abstractly, but we can use these Posnikov diagrams or alternating strand diagrams. So let me take one of these diagrams, and then I get a collection of K subsets. And for each K subset, I have a rank 1 module, one of these nice modules, and I just take the direct sum. And the claim is that this gives us like a cluster in Scott's cluster algebra picture. And in our language, it's a cluster tilting object. So it means like that it doesn't have any self-extensions, or that all its summands are compatible with each other pairwise. And it's also maximal. You cannot add any other summands which are distinct from those. So with that, we can show that the KN diagrams give us a combinatorial approach to these complicated Grassmannian cluster categories. What we really show is we take this module MD, we look at its endomorphism algebra, and we show that it is isomorphic to an algebra we get directly from the diagram. So this comes directly from the alternating strand diagram. Where you look at how these strands cross, and they give you, and you draw a vertex for each alternating region. And then they are connected by the way the strands go. That gives you the direction of edges between the vertices. Or if you take this algebra and specialize to the boundary, you get this the algebra given abstractly by Jensen, King, and Su. Okay, so that's telling us that the diagrams can be used to understand or give a combinatorial approach to the categories, but we can do more. We can look at the categories and objects in them. Every object can be filtered by the rank 1 modules. Let me say a few things about that. So that really means that there is a submodule which is one of our nice modules. And then if you look at that one, of course, that's also in the category, but also the quotient should be in the category. So it's not just filtered, but it's nice in the sense that if you remove one, the rest is still in the category. But in general, this category is not well understood. So what we want to do in the last part is describe some of the small rank cases and show how we get root combinatorics out of these modules. So to understand the structure of these categories, well, there are finite types. So when K is 2, it is like in the cluster algebra picture, we deal with triangulations of a polygon, and there are only finitely many diagonals. And this explains us the whole cluster algebra or cluster category. Or when K is 3, we have 3 more cases, and is 6, 7, and 8. So these are well understood. You find the description of the categories in the paper by Jensen, King, and Su. So in all other types, if I assume this, Fkn is of infinite type. The first non-finite ones are 3, 9, and 4, 8, which are tame, which means the indecomposable objects come in a one parameter family, or in one parameters families. And this can be described how they look like. And we really know how they sit together, all the indecomposable objects in these cases. That's joint work with Bogdanic and Garcia-Elsener, is that the indecomposable objects, they are not just a rigid, so you can also take arbitrary indecomposables. They sit together in tubes, which are well understood, and you know how big these tubes are. So that's, I wrote width here, it's really, that's called rank in algebra. So they will be rather thin of width 2, 3, and 6, or 2, 4, and 4. So these are the tame types. They have been known for a while, but then in all the other types, what we can show now is still that the indecomposable objects fit nicely together in tubes, which means you can start with some known objects, for example, the Blücher ones, and then build up new ones by considering short exact sequences. The tubes, well, before we knew the width exactly, right now we only know that they are a factor of this number. And then they can vary. You see here that they're not constant. Okay. So to understand the Grassmanni cluster categories, we first study rank 2 and rank 3. And then also consider link to root systems. So there is an associated Kac-Moody-Lie algebra or root system. If we take this graph JKN, which has n-1 vertices in a line, and then it has an extra vertex at node K. So this is of Dünking type when K is 2, because then we just have, we ignore this part, and you see that this is a type D, or 3, 6, 3, 7, 3, 8. So these are the finite types exactly, and the associated Dünking types are DN, E6, E7, E8. Okay, well, we have such a graph. This is a Lie algebra when we are in this finite types, but in general, it's just gives us a Kac-Moody root system. Let's consider the simple roots for these nodes, and then we can define the degree of a positive root to be the coefficient at node n. So the degree of alpha is the coefficient at this extra node. And what King observed is that in the finite types, the indecomposable objects in the category are really in correspondence with the positive roots. I should not say 1 to, well, it's a correspondence. Sometimes it's 1 to 1 when it's Blücher, but it's rank 2 modules. So it really depends on the rank. More precisely, if M is of rank S, there is a root alpha of degree S, and for each alpha of degree S, there are S modules. So it would be S to 1. Well, how does this work? So there's a way to take an indecomposable module. And remember, it can be built up from the rank 1 modules. Now these rank 1 modules come with K subsets. And to find a vector for M, I just count multiplicities. So X1 is how many times 1 appears in all these subsets I1 up to IS, etc. And that gives me a vector in z to the n. And in fact, it's in this sublattice. And in the finite cases, they are all roots for that root system. So you have to have a quadratic form, then you check that they all evaluate to at most 2, and exactly to 2 in the finite cases. So they're all real roots. But the question that King then asks, I mean, first of all, this correspondence is not so clear. It works in the finite cases. So the question is, if we take an indecomposable module, do we really always get a root in the associated root system, which has the right degree? And the second one is, if you take, say, a rigid module with such filtration, can you cycle the factors through? So if you start not with mi1, but with mi2 and put mi1 at the end, well, it's expected that it is still rigid and indecomposable. We know the root is the same. And we can give partial answers in the rank 2 case. So if the module just has 2 factors in the filtration, we know we can switch it, so we can cycle the factors through. The opposite one is also rigid and indecomposable, and the associated vector is always a root for that root system of degree 2. And we have partial answers for rank 3, but only when k is 3. And I'm running out of time. Let me try to finish. So just to explain a little bit more how these rank 2 modules look like. So I said they are filtered by rank 1 modules. Now our rank 1 modules were these lattice pictures on a cylinder. And in some sense, I just have 2 of those sitting on that cylinder. So at each of the vertices, I should have 2 copies of the center now. And the top one is like we did before with yellow and blue and everything below. But the bottom one sits a little bit lower, where we start with circles. So just the point is one-dimensional, but now I've had multiplicities. So this M246 is just sitting below the module with green and red. And then they're linked together, and you have to explain exactly how the x's and the y's act. But you can describe an indecomposable module explicitly with matrices and vector spaces. And then if you look at it that way, as a lattice picture, you see between the 2 modules, like you have the one starting from the circled vertices and everything below, and the one on the top, you have this gray shaded area, which is just 3 square boxes. And what we can show is a rank 2 module is rigid indecomposable if and only if these boxes are, if these areas are really boxes. So they're not allowed to do something like this in between 2 meeting points. That would be a quasi-box. So a box means rectangular. And then once we reduce this, the rigidity or the counting to having boxes, we can start counting how many such modules we have. And that gives us the formula below. And I think I'm running out of time. So coming back to the Postnikov diagrams is, I mean, in general, we took these Strand diagrams from Scott's paper, which are really explicitly given for the nice permutation. But if we want to look at other permutations or study other cells, we'd like to have an explicit construction to get them. We can take, instead of triangulations, we could take tilings in a disk, or we can take bicolored tilings, which add some color to the tiles and allow for more permutations. And then we can get degenerations. So that's work in progress. The degeneration part is work in progress of my student. the bicolor tilings are introduced in this article. And then it would be nice to have these alternating strand diagrams on arbitrary surfaces and study what kind of cluster algebras or cluster categories we get. And that's so far only working for triangulations. And we have some ideas for more general situations. Thank you.
Very good. So thanks so much for a great talk. I think we're not going to have time for any more questions. We'll have to refer because the next talk starts in 2 minutes, but let's all thank our speaker again.